Thank you very much, Dr. Tavin. Thank you very much, the committee, to be present and to be able to judge my work. Thank you, the audience. And I will start my thesis presentation. My title is Predicting Therapy Adherence, a Machine Learning Approach. I prepared with care and love this presentation, so I hope you enjoy it. So let me start. I want to start this presentation with one specific sentence. $300 billion were spent in the United States in 2017 only because of people who do not adhere to their treatments. And this took my attention a lot. And I really think that if we can save part of this $300 billion share, we can make healthcare more efficient and hopefully even more less costly, right? And through my thesis, I start to work with one specific kind of therapy, which suffers a lot from non-adherence to this therapy. And it is the obstructive sleep apnea therapies. What is sleep apnea? Sleep apnea is when a patient is trying to sleep, but their airway collapses and they cannot breathe anymore. So their brain sends a message to the muscle in their neck, making them cough while they're sleeping. So this makes them wake up. And if a person has more than 15 times these sleep apnea events per hour, they are likely to have moderate to severe sleep apnea. And there is a treatment for that, which is this mask here, which is a pump. It's this device, which is a pump connected to a mask that sends a positive airflow and helps patients to breathe while they are sleeping. But unfortunately, many of these patients do not adhere to this therapy, do not tolerate this therapy. But fortunately, there is an alternative, which is the UAS therapy, which is this device here, which is an implantable device that when it senses that the patient will have a sleep apnea, it stimulates the hypoglossal nerve of this patient, moving their tongue forward, allowing them for the air to go to their lungs while they are sleeping and help them to breathe, and they do not have a sleep apnea event. And the nice thing about this therapy here is that it is controlled by this remote control, which the patient can pause, start, or turn off the therapy, or even change the intensity of this therapy. But still, for both therapies, non-adherence is a problem. And what is the consequences of non-adherence to a treatment, to sleep apnea treatment? Well, the patients are likely to have higher blood pressure. They have higher chance to have a chronic heart failure, have a higher chance to have diabetes type 2. And also, because they do not sleep well, they are likely to go into depression. And even if you ignore all these 4 points, still $16 billion are spent only because of motor vehicle accidents linked to patients who do not treat their sleep apnea. And this sleep apnea was not the only type of therapy that took my attention during these years. There is another one, which is the growth hormone therapy. It's a kind of therapy that is completely different from the sleep medicine. Actually, it is a therapy in which kids need to inject in themselves using this device here, the growth hormone therapy. And by injecting this growth hormone therapy, they allow them to feel the deficiency of growth hormone. But still, non-adherence is a big problem, even in this therapy, because it really determines if the patient will reach their goals or will fail their therapy. And if the patient do not adhere to the growth hormone therapy, they will lose one in a lifetime puberty window to growth, which is the specific time in our life that we are likely to grow, right? So if they do not adhere, they will lose this mark. So this really took my attention. And when I talk about adherence, what exactly I'm talking about? Well, in the case of sleep apnea, if a patient use their device, can be the CPAP device or the UAS therapy, for more than 4 hours in at least 70% of days, we would consider them adherent to the therapy. On the other hand, for the growth hormone therapy, if a patient injects the prescribed dose in at least 85% of the days, which in a 1-week scenario, it means that the patient can lose at least at most 1 day, they would be considered still as adherent. And the nice thing about this work that I did is that there are many companies behind of each of these therapies that I was able to collaborate with. We have the mHealth Fairview, which is behind the CPAP dataset. We have the Inspire medical system, and also we have the Merck KGA behind the growth hormone therapy, right? So before I start to talk about the exact problems that I am going to talk here, I just want to emphasize one thing. Why right now is the best time for this kind of thesis, the thesis that I am defending here? The first thing is that imagine that you're a patient in the past. In the past, you would go to, like if you're sleep apnea, if you suffer from sleep apnea, you would go to a Ph.D. test in which we would collect data from the patient. And then you would go to some follow-ups. And in these follow-ups, we would collect data as well. So what we had in the past was that we used to have an episodic data collection. And what really changed right now and today is that we are now able to collect data, not only these episodes, but all the time with smartphones, smartwatches, and even the electronic device that is used for the therapy themselves, right? So what we are changing right now is that before, we used to have no continuous data or predictive model, so we had a reactive healthcare. But what we are able to do, and I'm going to show some of the tools to do that, is that now we are able to use continuous data analysis and machine learning models to provide to the healthcare a proactive approach. So now they don't need to be reactive anymore. They can be proactive in a sense that they can predict what is going to happen and act earlier in the therapy without something worse happens. So what are the problems exactly that I'm going to talk in this presentation? I'm going to talk about 3 problems. The first one is identifying distinguishable therapy usage patterns for early intervention. And for that, we are going to do cluster analysis to the UAS therapy. And also, we are going to answer one question. How does patients migrate from cluster to clusters, from different patterns of therapy use to other different patterns of therapy use in the CPAP therapy? Then I will provide a tool, a framework, to predict therapy adherence for a fixed time interval. And this tool, the name is CTAP, which means Continuous Therapy Adherence Prediction. And I will apply for the CPAP therapy and for the UAS therapy. And finally, the last problem is that instead of predicting adherence at a fixed time interval, we are going to predict adherence in a near future time interval. And for that, we have the TGap approach, the time generic adherence prediction, in which we apply for the CPAP, UAS, and growth hormone therapy. Okay, so let's start the first problem here, which is identifying distinguishable therapy usage patterns for earlier intervention. In these visualizations that I'm showing you in this slide, we have three types of patients. And this visualization I was able to develop with Inspire, the company behind the UAS therapy. And each line here is 1 day of therapy usage. And you can see for this first patient here, which we call the textbook patient, that the patient starts the therapy at almost the same time. And we have these green bars here that represents the amount of time that the patient used the device during the night. And you can see that for this first patient, this patient really used the device quite well, and also turn off the therapy quite in a consistent amount of time, in the consistent timing. But now look at this second patient. Although it starts using the device quite good, we see these purple regions here in each day of therapy usage. And these purple regions means that the patient is pausing too much the therapy and using less the therapy. So something is happening with this patient that they are pausing the device. And then we have the irregular therapy time type of patients that we found, in which you can see that although this patient do not pause too much, it is really inconsistent in the time that they are turning on the therapy and also the time they are turning off the therapy. And even there is some gaps in the therapy. So we found these three types of patients by a qualitative analysis using this visualization, but we want really to perform a quantitative modeling of this therapy usage. And that's why we came with the cluster analysis. And how did I do that? I got a data set from UAS, of UAS therapy from Inspire with 2,091 patients. And we look at data from day 1 to day 9 of these patients. And we extracted 11 features from each patient that would represent these patients. And what are the 11 features? Are the mean and the standard deviation of the therapy hours, the amount of therapy hours, the number of pauses, the percentage of missing days, the time they turn on and turn off the therapy, and also the difference of the amplitude between the day 90th and the first day. So we extract these features, we perform a z-score normalization, and then we picked a Gaussian mixture model as a cluster algorithm in which we tried different number of clusters, and we found that 6 would be the best number of clusters as the parameter for the Gaussian mixture models. And then we fitted the model, and we computed the centroids of each one of the 6 clusters. And the centroids of these clusters are these ones that I'm showing this table. Each column here is one cluster, and each line here is the mean value of the feature in each cluster. So let's take an example. We have the cluster 1A, which is the cluster with patients with excellent use. And in average, they use 7.2 hours the therapy. In the other hand, we have cluster 3B, which is the cluster with the lowest therapy usage. And in average, they use the therapy for 5.5 hours. Actually, although we found 6 clusters, there is 3 main types of clusters. We have the excellent users, which are the cluster 1A and 1B, the good users, the 2A and 2B, and the variable users, the 3A and the 3B. And these variable users, which are these 2 clusters here, are the ones that we should take more attention, right? And why? First of all, they have the smallest mean of therapy use, but also when you look at the cluster 3B, you see that they have the highest number of pause per night. So patients in these clusters, in average, they pause around 5 times per night. And when you look at cluster 3A, we have a different pattern of usage. They do miss many of the days, in average 34% of the days they do miss in the therapy. And also, this is very interesting. The standard deviation that they turn on and turn off the device is very high. So they are very inconsistent. And that's why we call them variable use. What is nice about this approach is that we could collaborate with sleep doctors. And we found that each cluster could have a specific kind of intervention. And this is what I show in this slide here. So we collaborated with three institutions, sleep institution, and the sleep doctors in this institution, they did help to hypothesize the interventions for each cluster. From the cluster 1A, that no intervention is needed because we really have an excellent use, no need for change, until we have interventions, recommendations for intervention for cluster 3B, which is the one that we really want more close attention to these patients, right? To patients in this cluster. All right. So this was the first part of problem 1. And now I want to change the topic. I want to answer one question. How patients do migrate from cluster to clusters? But now, not talking about the US therapy, but talking about the CPAP therapy. In the CPAP therapy, we also collected data of therapy use. Now we are talking about 1,815 patients. And we look at data from day 1 to day 180. And what we did was that when we visualize the mean therapy use and the standard deviation of therapy use of patients in the 60th month, this is what we see. If each patient is one dot, and in the x-axis we have the mean therapy use. So I even put here a red line showing a reference of the 4 hours. So anything after the 4 is, well, a good therapy use. And then the y-axis, we have the standard deviation, so how they vary in their therapy use. And again, we use cluster analysis. In this case, we use k-means with k equal 4. We found that 4 would be the best number of clusters. And we found these 4 clusters. We found the red clusters and the yellow clusters, which are the clusters that we don't like because they have low therapy use. And in the case of yellow, they also have high standard deviation. And then we have the cyan and the blue clusters, which are the clusters that we like because they have high therapy use. And we really like the blue one because they have high therapy use and low standard deviation. So they are very consistent on high therapy use. So what it was nice to answer that question is that we colored the patients and we look at how they would change their patterns over time of therapy use. So we fixed the color using as reference the first month of therapy. And then we look at how they would migrate to other parts of this chart over time. And although it's not very clear in this visualization, we visualize that patients in the red clusters and the blue clusters, they tend to stay there. And the ones in the cyan and yellow, they change a lot between these clusters. So this was a qualitative visualization. And then what we provide also was a quantitative information about how patients change to these clusters. And what we used was Markov chain analysis to compute the transition probability for that. If a patient is one cluster, what is the probability for this patient to change to another cluster? And we found some very interesting things. The first thing that we can see is that when you look at the diagonal of this matrix, you will find the highest numbers, which means that if a patient is in one specific cluster, it's likely that they will stay there. But then we have this we noted that when patients are in the intermediary clusters, that which is the yellow one and the cyan one, they are more likely, and this is a good news, they are more likely to change to a better clusters than to change to a worse cluster, to go back to red or go back to red or yellow in the case if the patient is in the cyan one. And finally, like in the case of the blue cluster, they only have 5% to go to probability to go to red or yellow, which is very low. And this result only reinforces the importance of, as soon as possible, try to put patients in the blue clusters to if needed, make intervention to make patients to stay in the blue clusters, because they will be likely to stay there. All right, this was problem 1. Let me now talk about problem 2, which is predicting therapy adherence for a fixed time interval. Now let me show again some data about the CPAP dataset that I have. I don't have only the therapy usage. Actually, the CPAP device provides 4 values for every night of the patient. We have the usage, we have the residual AHI, we have the pressure, the air pressure, and also the air leakage of the machine, from the machine. And this is one example of a real patient that went from day 0 in their therapy, and this is their usage, until day 180. And what is important here that I'm highlighting is this target period here, which is on the 60th month of the therapy. So the problem that we have is that we want to predict before the target period if the patient will or will not adhere in the target period. And why this target period is important, right? Why we're concerned about that. And the reason is that some insurance companies, they check if the patient is adhering that specific target period, and if they are not, they will not pay or will not cover the treatment. So it's very important that if we predict that a patient will not adhere in the target period, that some intervention happens, so we change this negative future outcome, right? And another important thing here that I want to tell is the class distribution. Actually, in our data set, 40% of the patients do not adhere in the target period. So our job is to predict them before the target period. In the same way, for the UAS therapy, we have many signals for every day. We have therapy usage, the time they turn off, the time they turn on, the number of pauses, the missing days, and the amplitude. And our job is to use this information to predict if the patient will or will not adhere in the target period. But in the case of UAS therapy, the target period is the 4th month. And we use the 4th month because it's known that if the patient adhere in the 4th month, it's likely that they will be adhering in the long term, right? The class distribution is a little bit different. So 69% of the patients do adhere to the UAS therapy, and 31% do not adhere in this target period. Using the definition of using the device more than 4 hours in at least 70% of the days. So this is when I came with the CTAP. The CTAP approach, which is continuous therapy adherence prediction. In this approach, what we want to do is not to build just one model, but to build one model per day from day 1 of the therapy until the day before the target period. In this case, we would build 150 models for the CPAP therapy. So each arrow here I am representing is just one model that is trying to predict, that is going to use all the data from day 0 to day that the model was created to make the prediction. And how do I do that? What is the methodology behind this CPAP approach? From the raw data, I pre-process the data, and separate it in a test set and a train set. And we start this loop here for every day, in which since day 1 until day 150, we get the data from the patient from day 0 until the day we are creating the model for. We extracted features from the time series of each patient, and then we train a machine learning model to predict using the target period. So we perform this loop 150 times until we have 150 models, and then we test and evaluate them with the test set. And just a little bit about what kind of features do we extract from this time series. Here we are talking about computing the mean, the standard deviation, the slope, and the correlation between those features from day 0 to the day the model was created for. And in total, each patient would be represented by 18 features. All right, here I'm showing one of the nicest results that I have in this problem, which is the average AUCPR score. And the AUCPR score is as high is better for the machine learning models that I trained. So each curve here, each colored curve is one machine learning model. All of them but the blue one. The blue curve is the baseline. And what is the baseline that we use for comparison? The baseline is what the clinics use right now to predict if the patient is going to adhere or not. And it's based on the definition of adherence, but using the data until that day. So for example, if the day 30, they use data from day 0 to day 30 and check the definition of adherence. So they use that as prediction for if the patient will adhere or not in the future. And what we can see here is that all of these curves are above the baseline. And actually, the random forest, which is this brown curve, is the best one. So the random forest was the best machine learning approach. And we can also conclude that we can make predictions since day 1 of the therapy using this approach. Now, let me talk about, now I'm going to present some results comparing the CPAP approach and the CPAP UAS approach. But first, let's talk about these metrics here. I will talk about the sensitivity of these models. And what is sensitivity? Sensitivity is basically how good the model is to predict non-adherence, right? So it's the recall of the positive class, and the positive class is non-adherence. In the other way, we have specificity, which is how good the model is to predict adherence, right? To separate adherence. So which is basically the recall of the negative class. And also we have the area under the precision recall curve, which is this metric AUCPR score. So when we compare the approach for the two therapies, the first thing that we note is that the best machine learning model is not the same for both therapies. Actually, random forest is better for the CPAP therapy, and logistic regression was better for the UAS therapy. Second, we found that the sensitivity for the CPAP therapy was higher than the average sensitivity for the UAS therapy. On the other hand, the specificity was higher for the UAS therapy when comparing the specificity for the CPAP therapy. And lastly, we have the AUCPR score. I also showed here in gray, the gray bars are the respective baseline for each of these therapies. And when we look at the UCPR score, we saw that our approach is much better than the baseline, right? When you compare these two bar charts here. All right. So what are the applications of this? What kind of application can we do with CPAP? The first thing that we notice that when patients are visiting the clinic, they can visit at any day before the target period. And for example, if this patient here has a follow-up on day 13, we can get their data until day 13 in the therapy, give to the machine, to the CPAP approach. We are going to have a model for that. And this model will give back to the doctor the adherence probability for this patient. And if the adherence probability is too low, the doctor will have a chance to make an intervention and change some parameters in the therapy to help the patient to tolerate more and use more the therapy. In the second case is that we can create a priority score for telemedicine. So this telemedicine is when the clinic predicts that the patient will not adhere to the therapy, and then they call them. So we can use the probability, the non-adherence probability, which is the output of our model. And we can also give a weight for how good the model is in the day that we are predicting this non-adherence. And also we can normalize by the day that the patient is in the therapy to come with a score. This is just one example of a score that we can compute that would take into consideration the time the patient is in the therapy and the probability for them to non-adhere to the therapy. This was not validated yet. We really want to validate this formula in future studies, but this is just an example of application of CPAP. All right. Now we have problem 3. Predicting therapy adherence in the near future at any time in the therapy. So what we are going to do now is not predict for a specific time interval, but given that we are in the present here, and in this gray bar is the therapy, the timeline of the patient, we want to use past information and give this past information to a machine learning model, and this machine learning model will predict how will be the adherence of the patient in a near future. And this near future can be the next 7 days or the next month or next 30 months. It's a parameter of this model, of this approach. And the amount of data that we give to the model is also another parameter. How does this is what I call the TGap, the time generic adherence prediction approach. And how can I train a machine learning model that does this? And what is the core idea of the TGap is the therapy segmentations that we do on the training set, on the patients on the training set. Because imagine this patient here. We have data from day 1 to day 561, so it already used the therapy for a long time. And then we can segment their therapy into pieces, these segments. And each segment has a blue part, which will be the past part that we are going to give as input to the model, and the red part, which is from where we are going to get the label if the patient adhere or not in that specific part. So our approach uses this the blue parts as input to a machine learning model, and in this case, what we are talking about is a deep learning neural network. So in this example here, we are using 180 days to predict the next 7 days. So we give as input 180 values to the model, and the model will, after trained, it will be able to to pass through this information through a recurrent neural network layer. And in the end of this deep learning model, we are going to have the probability of non-adherence of these patients. And for this approach, what we do is extract segments from patients, right? And in the case for CPAP, we extracted 1,242, we have 1,242 patients, and we extracted 2,620 segments from them. In the same way, we have the test set with just a little bit less number of patients. So it is important to tell that there is actually three main parameters in this approach. The first two, I already told you, is the past size and the future size. We showed here how good is the model when we vary the future part and the past part. And I highlight here that I choose to use 180 days to predict the next 7 days. And actually, you don't need necessarily to pick the highest number here, because this parameter really depends on the context of the therapy. I picked it to predict the next 7 days because my idea was to use the model as a notification app, a notification application that would give notifications every week for a patient, and then they could check in their smartphone how if they are going to adhere or not, or we could even provide some recommendations for the next week for this patient in the case that they are not going to adhere to the therapy. The third parameter, which is something very important that I really want to highlight here, and I discussed a lot in my thesis, is the positive class weight. What is this positive class weight? Is how much attention the model will give to how much weight the model will give to the positive class, to when it sees a non-adherence example, how much weight it gives. And why this is important? Because when we vary the positive weight class, and I'm showing here these curves, on the red curve is the sensitivity, the blue curve here is the specificity. We see that sensitivity is very sensitive to this parameter. But the AUC ROC curve, the AUC ROC score, actually, which is this parallel, these two parallel lines here, the AUC ROC and the AUC PR, they do not, well, at least just looking, they do not change that much. And this is a problem. Why this is a problem? Because in many machine learning papers, we only see people reporting AUC ROC or AUC PR and telling that their methods are better than others just because of that. But they do not report sensitivity or specificity that much. And especially in the healthcare, sensitivity is very important, because if you have a low sensitivity, you have more false negatives. And false negatives in healthcare can be, for example, if you have a false negative of a model that predicts a disease, or even like predict cancer, false negative can be life-threatening, right? So we should really care about that. In our case, after we provide this cost-sensitive analysis, we found that the weight 1.75 would be the best for us. Now let's answer some nice question here that I really like to do this experiment. The first one is, does the performance degrade over time? So is our model good on predicting segments in the first part of the therapy as good as in the, like after 2 years in the therapy? Yeah, and actually the answer is yes. We do not see a degrade in the performance. You may ask, okay, Mateus, I see a low sensitivity here and a high specificity in this last part when we are predicting segments on 2.5 years. But actually, this is probably just random fluctuation, because we do not have too many examples in this time in the therapy. This is the number of segments, this black line here. So we have very little examples. So probably this is just a random fluctuation of that. The second question is how much each day contributes for the prediction in the model. So in the days that I give here in the past part, how much each day there contributes to the model. And we can see as we go close to the present, the importance of the days grows exponentially. The days that are close to the present are the ones that are more important for the model. Now, when we compare the TGap CPAP approach and the TGap UAS approach, what we can conclude? The first thing is that after combining the past size and the future size with different numbers, we found that usually for the CPAP, we have a higher AUCPR score, and the UAS is slightly lower. But the second thing, which I think is also important, is when you look at the ratio gain, basically dividing the how good is our model by the baseline. So we see how much we are gaining by using our model. We would see that the ratio gain for the UAS therapy is a little bit higher, is 1.44 in contrast of 1.34. And in the end, what we can conclude is that TGap really unlocks the ability to anticipate low adherence at both therapy, and we can use at any time in the therapy. Now, I told you about growth hormone therapy, and we had the chance to use the same approach, the TGap approach, in growth hormone therapy. This was a collaboration with Merck, and we have access to 2,500 patients, and the average age of these patients are 10 years old. And from then we extracted 7,907 segments. But the configuration was a little bit different. Now we have a configuration of 6 months of therapy predicting the next 3 months of therapy. And this is only because this was what Merck thought that would be more interesting for them. So what are the conclusions that we came? We use the same methodology, basically. And when we look at how much each day contributes for the prediction, we saw that a less sharp exponential curve, right? When we compare to the CPAP result, this is much more sharp. And for the growth hormone therapy, we can see that is less sharp, which means that the contribution of each day is more evenly distributed, but still, as close you go to the present, much more important is that day for the model when the model is predicted. When we talk about performance, still the performance of our approach is better than the baseline that we computed for them. They really like that. And what else I want to highlight is that this was a great collaboration with this institution, Merck KGaA and TNO. And we also, in this last point here, we observed the generalization of TGap to go beyond sleep medicine, right? In this case, we went to endocrinology, right? All right, I am going to my concluding remarks. The first thing that I want to do for this conclusion is to tell what this thesis really does, right? And the point of this thesis is to fill the gap. And which gap? When we have a patient generating data, these data are now stored in hospitals and health clinics, and all this data is stored there. But what this thesis really does is to perform a data analysis and use these models to provide personalized therapy insights for the therapy managers, for the doctors, for the physician, so they can make therapy adjustments and the interventions on those patients who really needs. So we are closing this loop here. And what would be the contributions to computer science? The first thing that we can note is novel techniques, right? In the case, for example, of TGap, we are on the top of state-of-the-art machine learning algorithms. We are providing new techniques like the therapy segmentation to solve this problem. The second point, which I think is one of the most important, at least personally, is that when we are able to show the value of computer science and what we can do with the models that we have to others from different fields, and when they understand what we are doing, much more resources will go to computer science. So I think this is a contribution to computer science. The third point is a deep discussion on the importance of choosing the correct metrics when we are reporting the models. I talk about the cost-sensitive analysis. So I really think that this is a nice contribution. And the last one is the data visualizations that we developed, right? Because the data visualization really helped me, at least, to find the best techniques to solve the problem that in a quantitative form. And what are the contributions for healthcare? The first one, and the one that I really think is the most important for healthcare, is that by using the data-driven models that I'm providing to them, the physicians now can be more proactive instead of reactive, right? They do not need to wait the patient to say, okay, now I do not tolerate any more CPAP. They can act much earlier with the patient, and as early as possible is easier to change the patient behavior. And then also we promote the use of already available data sets, because these data sets are gold mines that healthcare practice have in their hands. The third one was to define well the problems of fixed time interval and near future therapy adherence prediction. And the last one was to show techniques that are applicable to like 3 different medical therapies from 2 completely different fields, sleep medicine and endocrinology. Now, these are my 2 last slides. And what I really want to reinforce here, I'm showing actually, right, the research that I did, the publications that we made. But more important than the title of the publications are that I'm highlighting here the partners behind these publications. And also in blue, I'm showing the computer science, the publications that were published in computer science. And the red, I'm showing the publications that were published on health sciences. And what I really want to show is that I'm trying to contribute for both, to build this bridge between computer science and healthcare, so we can help them, right? Show our value to them. And all right, these are my last set of publications since my proposal defense. Now these are in 2021, in which we have Merck, again, Inspire, Fairview, mHealth, and yeah, everyone, and also contributing to both computer science and health science proceeding. This is my presentation. This was my presentation. I really want to thank you, the committee, the audience, my family, my friends, and my wife. Thank you very much.